And Rifki, today at 12 o'clock, I have a meeting with the psychology department. So, but I'm in class too, so I'm not sure what time I'll be able to finish. I'll try and be there early, but go to Said's office at later on and see if he's free. That then he can meet them in front of my office at 12, just in case I'm late. Or otherwise, you can meet them there and just say that I'll be a couple of minutes late. If I'll try and be there on time.
For the undergraduate student?
Huh?
For whom?
It's the psychology department. To professor and a postdoc from the psychology department come to talk about. Pardon?
They will visit the lab?
They will visit the lab later on, yes. But I think they're going to be in front of my office. They said they're going to come to my office. So just see if you can meet them, or if Said can meet them, of course. Actually, I better send a message to Said, tell him that we have that meeting. I'm not sure if I told him. Oh. So this is the scene that I set up. Nothing spectacular. Pen. And now I actually knew how to do that. With the Python interface, you can actually find the image coordinates of the various objects. But there were some little caveats that you had to take into consideration, in particular whether the scale was applied or not and whether the rotations were applied for Blender. So I'm going to do this the easy way, and we're just going to open the image in open the image in Krita. And then we can use so that's 264, 264 and 255 for that center turn right marker there, right? So then let me upload that image. And then the center coordinates, what did I, 264 by 255? 264 is one of them. The other one is 6163. One 6648. And I think I got this one wrong, right? This one was 163. 60, and the coordinates are y and x. And then we have 41246. 516 155. Okay. Then I also uploaded to Oh, how do I upload it? Uh, so let's have a look and plot the areas that we covered. So I set the markers are at these locations. And we can convert that to a NumPy array already, because that will come in always useful. So that would be markers, comma 1, comma 0, size is equal to 20, color is equal to red. ax.imdraw. Then I have to load it first. or resizing. Image draw. What is it called? Image show. Then the colors may be off. No. Okay, so I got the centers reasonably close here. Right. Now I want to draw the bounding box. For x, y, x, for mx, my in markers, then we need to cover the xy coordinates first. So that would, now there should be my, mx. Be and let's try 32 pixels first. Integer mx minus marker size divided by 2. My minus marker size divided by 2, the integer this. Then I think it needs width. So that should be marker size. Marker size. And then fill color, edge color equal to red. ax1 dot add patch R, I think. M patches. Marker size. Okay. Quite a bit too small here. So let's make that 128. Okay. Too big. And fill color is equal to none. what is it? Matplotlib rectangle fill color. Color. Just color. Okay. No. So how do I filled equals none, filled equals false maybe? Fill, okay. Okay, then we can make the our bounding box a little bit smaller. How about 80? Let's shift that one over. So that was the first one, 260. So this is just a quick and dirty setup to be able to have some bounding boxes so that we have some images of the markers as they may appear to the robot when the robot is walking, right? Now, this is not going to fit the images from the robot exactly, but it's giving us some test data that we can start working on. Furthermore, it makes it, once you have your Blender file set up, with the Python script, you can generate an infinite number of these test images. And like I said, you also can actually extract this bounding box here exactly. I just forgot exactly how to apply the world transform. Basically what you have to do is you have to apply the various matrices to the coordinates. Like I know where the coordinates are for the object in real world coordinates. I need to project them to the camera coordinates, which means that I need to apply the world coordinate system and the perspective camera translation. And then you can read out what the pixels are for each corner. That works nicely. It'll give you a tight bounding box. Now I just did it by hand. If you only have to do a couple of them, that's possible. But of course, if you generate an infinite number of them, you need to use a script to be able to do that. So now, any suggestions about how you would track these objects?
The images are black and white. The objects are going to be black background, white arrows.
Yes.
So
Actually, I'm not 100% sure. I think in the rules it actually says that they can be white on black or black on white. But they won't have any color apart from white and black. And I think yeah, I think it says in the rules could be either way. But okay, fine. Let's say they are black on white. I mean white on black. Well, let's assume that the arrows are white and the markers are black.
So detect all black objects.
But if you remember my first couple of classes, we talked about color detection, right? And the whole point of these classes was to try and convince you that this is a bad approach. If you want to detect color, if you want to use color in your recognition pipeline, then the time to apply it will be at the very end. So you would be thinking about trying to design an algorithm that can detect the shape of this, right, is reasonably sure that this is a marker or a ball or a basket in basketball or the bar in weightlifting. You're already pretty sure. And then at the last instance you say, okay, well, I think this is a marker, but let me just check to make sure there is nothing really red in there, or really blue, or really green, that this is basically a grayscale color part. And that you can do. But at that point, you're already 90% sure that this is a marker. If your first step on your vision pipeline is, I'm going to detect red, I can guarantee you it's going to lead to failure unless you have complete control over the setup and the lighting of the scene. If you design a machine vision system, right, and you have a conveyor belt of widgets moving along, and you're supposed to detect how many widgets are coming or what color the widgets are, then you can use color, because you can install the lights, you can set up your camera, you can make sure there are no shadows, and then, yes, then it'll be the cheapest and easiest solution, and it will also be quite robust in that sense. In a dynamic environment where you have no control over the lighting, outdoors, it is a fool's errand to try and find a color predicate. And it doesn't matter what you use, HSV, YUV, RGB with the difference channels, like we use, if we do use color, then we use RGB with the difference channels. But it is never going to work. And you can ask my marathon students in Kaohsiung. Like I said, it was very exciting. We were chasing the world champion for a good 30 meters. And then the sun went down and then our color calibration was off. And then students, instead of our robot walking the marathon track, my students were sitting there trying to calibrate the colors for the track. But the problem is it's sort of an incremental process then, because if you step off the track, you get a 5-meter penalty. So then you can calibrate the color 5 meters before you actually reach that point, and then you can get there, but then you fail, then you get pushed back another 5 meters. So we don't want to use color. So if we don't use color, then we really have no other choice but to use the shape, right? And by shape, we could do something like this. Like at the very beginning of the class, we applied the, which feature tracker? Harris corner detector to the image, right? So we could apply corner detection to the image. So try that. Just apply the corner detector to the sub areas that we found. Or actually, you can run it over the entire image. Then that gives us also a good idea. So I'll ask you to copy this notebook and then apply the corner detection to this particular image, and then try and find parameters that are reasonable for this particular image. What do I have there? It's because I have the cursor there still. Okay. Yes. So slides. Oh, and I posted it to the wrong channel. Where's ERC? So now I have the corner points. I just need to figure out how I want to paste them into the image. So there, I could say image corners greater than 0. Is equal to and let's make that green. Assignment destination is read only. So how come this is, actually I'll turn off the dilate. Oh yeah, to see it, it'd be better to dilate it. Okay, so I think we can only copy Okay, so here we have that. So that would be CY, CX, and the value. Image CY, CX is equal to corner mark. So do I need a okay. And then I think okay, I found some corners there, but not on our markers. So we need to play around with the images. So let's show corners. there. And here we want a larger block size because we have more pixels. So four and five and five, 4 and 5. Okay, so now we have more corners also in our areas here. I can set that a little bit. Six. We're not dilating anymore, okay. And then now I think I can change this one to here. Okay, good. Then here would be our corner detection for the various marks. Now looking at that, it's I feel that we don't have so much data now for the markers. Uh, the corner detector now is actually pretty sensitive, so it did give us good marks there. Didn't give us anything in the remainder of the image, which is kind of nice. Probably not likely if we have a real environment. So my feeling would be, or if you think about the same thing, then probably you would say that there's really not that many corner pixels that we get out of the marker in order to be able to distinguish marker from not marker. And then once we have the marker, we would have to find the orientation of the marker as well as the type of the marker. So we need the position or the rotation of the marker as well as the type of the marker. And my feeling will be that just looking at the corner points is a little bit too limiting. It may work, but even at the front marker here, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different corner points. Now, also when you look at the image, then here we have none. In the shadow, here we have a couple, here we have a couple. Now, here the result is not that good, but that's probably not such a big problem because the robot really only needs to identify that there is a marker, then walk towards it. If it can do that, then as it walks closer, eventually it's going to get a better look at it. So let's turn that into a slide. What is it? Axis of. Ah. So this is what I get for my corner detector. Let me have a look at yours. Show the corners. Okay. What are this?
I don't know.
The red one. Okay.
Actually, I haven't started here.
Okay. Then you can do the next step. I think if you look at the pictures, then even the picture here in the bottom, it doesn't really give us that many corner points, right? So I think it's probably not such a strong feature to then group together and try and match to certain pixels. It may work, but my intuition would tell me that probably we would like to have more relevant data, right? That allows us to track the objects. So, what else can we do? So the corners may be too specific for this particular application. The front one actually we can recognize and register pretty nicely if we get those corner points. More concern are the ones over here. And over here where we don't get any pixels, any corner points. Here we also don't get all the corner points. So what is the detection of the corners based on? How do we decide, how does the corner Harris detector actually, the Harris corner detector actually work?
Highest gradient, next gradient line.
Correct, so we're looking at the gradient, right? It's not actually the highest gradient. We are constructing the matrix of the gradients, and then we're looking for the eigenvalues of that matrix. But And the basic point is that we want to have a high gradient both in the x and the y direction. Right? High and similar gradient. So I think probably it may be a good idea to here not just pick the corner points, but also pick the other points and include them in our classifier, right? Like here I have all these pixels, even on this center marker here, which the right turn marker here, where we get a lot of good corner points, there's all of these pixels that we don't really include in our decision. And that seems to be a not such a smart thing to do. I would like to include them, and the way to do that would be to look at the gradient directly, right? So instead of basing our classifier on the corner points, we would base our classifier on the gradients in the image. And in a sense, that's even easier to implement. That just means I need to run the Sobel edge detector in the x and y direction. And so let's see how that would look like. So now I want to design a function for detecting the edge points. I won't actually be marking them anymore, so I don't need the corner mark thing. But we're gonna do some special processing with this. So I'll take the image, make a copy of it, and this. So I probably want to use two images here. Yep. And that would be this is gray. then I just need the parameter source. So that would be image. Dx dy. So I'm not sure what d depth is. Oh, the size of this. Did I even specify that? Dx is 1, dy equals 0, case 3. And Sobel y is 0, 1. And let's just see if that works. Can I just... Sine 16. Okay, it's... Case size. Okay. Case size. Okay, and here, of course. So now I get the gradient, Sobel, the output of the Sobel edge detector in the X and Y direction. What information of that would be the most useful in order to identify our markers? Or, in other words, I have an image, right, of a tree. And now, when I calculate the Sobel, when I run Sobel edge detection on top of that, then I basically get the derivative and here I would have a strong response. In the X and the Y direction. So that basically means for every pixel I now have two vectors. Pointing in the X and Y direction, telling me the first derivative of the image function in those directions. Now, based on this information, what would be useful in this scenario in order to be able to detect my marathon markers or detect a tree or any other kind of shape? Well, if I have two vectors, what can I actually calculate? Angle, yeah, right? So that would be this angle here, and oh, so close. The magnitude, right? Yeah. Right? So those are the two pieces of information that we would get out of calculating the gradient. Now, if we want to detect the markers, then I would say, lots of other people would agree with me, I think it makes sense that we would be mostly focused on the angle of the gradient rather than the magnitude, because the magnitude will vary greatly between the marker being in the shadow and the marker being under the bright light. In that case, the edges are going to be more crisp, right? There's going to be a much bigger difference between the white and the black areas if the scene is well lit as if the scene is in the shadow. So the actual length of this vector, the magnitude of the gradient, can change quite a bit, but the direction shouldn't change that much, right? Because if the marker is in the shadow, all of the gradients are going to be smaller, lower, right? All the responses are going to lower, but the direction should be the same. So now we want to calculate the angle of this gradient, and how do we do that? It will be the inverse tangent of dy and dx, right? And so now we want to apply that to the image. Now I want to Of course, I could calculate that by hand. No, not by hand. I could calculate that using primitive operations. So there probably is a numpy.8tan2 function or arctech2 function that I can use. Actually, why not? There's also a polar to Cartesian coordinate, two polar coordinates. So I can actually pass in those two images here and then get as output the polar coordinates, which would give me, of course, the angle in one of them. So the arctang2 of Sobel y and Sobel x, I guess. And I just have to make sure I'm not dx1, dy0. That should be the whole x, the Sobel edge detector in the x direction. X order 1, yeah. I just want to make sure these are correct there. So now I get an angle. Now I want to color that angle somehow. Right. Actually, let me make sure I get the angle. Yeah. And oh, I just return that and plot it. Now this should be, let's hope for the best. This is AX1, AX2 is equal to at subplot 1, 2, 2, AX2 dot IMShow and this now. Zero to 1, so I need to normalize that image. So I divide it by the maximum. Hey, how come? Let's see what we get. .350 by 658 by 4. Okay. So that means, because I need to apply it to the grayscale image here. Okay, now we have a false color image here. is angle still 4? Angles. Name angle is not defined. Oh. And here I want to show the data type too. Float 32000, yeah. Okay, and so here we have the output. So now for every pixel I get some data, and it actually is kind of correlated to what we need to know about the marker. The green, I could set the color map here. And for that, turn the axis off too. And let's have a look at the matplotlib color maps. Sequential, okay. So how about plasma? No, I think CMAP. Okay, let's try that. AX2. Oh yeah, that way I can change it. Cool. And what looks kind of cool is that this area here in the front, we actually had a change in the direction of the gradient, but that's really because there is a very small gradient here, so that's kind of then over amplified. So we could, if we, what we could do is convert it into polar coordinates and then only apply, set everything where the gradient is below a very small threshold automatically to 0, just to make sure that all the areas that are uniform also show up with the same gradient of 0 degrees or something. Because we cannot, we have, like, even if it's constant black, right, I need to return some angle, and even though there is no gradient. But at the moment, we'll focus on the markers here. So now I have the marker. Now what? I mean, now I have the gradient. Now what would I do? And what happened there? Well, my next approach to trying to find the trying to define the markers would be some kind of histogram-based approach where I look at different areas and then I simply calculate in which direction does the gradient actually point. And if I have an area that has mostly a gradient going downwards or vertical, then I will calculate all of those. So we have discussed histograms before where we looked at the average color or the sum of the pixels in a particular region. But now what we're getting is angles. Right? So now I sum up for each region in what direction does the gradient actually point. How many gradients point, or how, for most of the pixels in there, in this area here, for example, there will be quite a lot of them that point in the horizontal direction. Here, there will be a lot pointing at 90 degrees. Now, this kind of makes sense, right? And in fact, it has also proven itself in practice. If you follow this approach now a little bit further, right, then what challenges do you have to overcome, or what decisions do you have to make with respect to your feature detector or object detector? So what I want is a particular area in the image now, right? And I get a whole lot of directions here. And for each one of my pixels now, I have an angle. Now I want to come up with a summary measure over all the angles in that particular region, right? Because in order to detect the marker, I'm looking at the relationship of all the pixels in that area. Now if I have an image with different pixels, right, then I would have the sum over I, x, y over particular areas, right? So I would sum up all the pixels here. And I can do that for the red, green, and blue channels. But what do I do with the angles? Well, let's say the angle is from 0 to 180 degrees, because I don't really care if we're moving from black to white or white to black. If my gradient is, and then that automatically would take care of if the marker is white on black or black on white. If I normalize my angles to be between 0 and 180 degrees, so I map everything to that range, then that means that I take the absolute of the angles, then that means white to black will be 0 degrees, black to white would be 180 degrees, and will be mapped to the same thing. But now we need to do the same thing as we need to do here. We need to define different buckets, right, in order to add up. So let's say I do 45 degrees, 90 degrees, 45 degrees, 90 degrees, 135 degrees, and 180 degrees. Right? And then I simply want to add up the number of pixels that I have. So if here, this would probably be more than 45, but less than 90, so I would have 1, 2. This one will be 1, 2. These ones are going down, so I count them as going up. And we'll look into those in a little bit. These ones here are horizontal, so I count them. these are going up, these ones are going down. So then let's say I have another couple of these here. I would just add volts into the buckets there. Okay, so the first problem that we have is to identify how fine or how coarse my counts are going to be here. Right? Because if I could just use two, right? 0 to 90 degrees or 90 degrees to 180 degrees. That would be one way of doing it. Or I could make a finer grain. 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, right? So somehow this discretization is an important step in any kind of histogram-based computations, right? Because we're basically looking for the signature over these buckets, so the way that we define the buckets is kind of very important. Now, the first problem that we would have would be the vertical edges here, right? Because let's say I have one that is like this and the other one that is like that. Then that's almost the same direction for the gradient, but because my border is 90 degrees, one will be counted here, the other one will be counted there. So then that means a tiny shift by a tiny rotation by the image would lead to a very different signature, which is not what we want, right? We want it to be robust to rotation. So how can we deal with this particular problem? There's a couple of alternatives that people apply to that. Usually, or most commonly, there is the idea of having a boundary zone. So if my buckets are 45 degrees, then maybe from 80 to 100 degrees, I make my buckets overlap. So that means if I have a pixel here, it will be counted in both this one and this one. So if anything is in the border region, then I simply count it twice. That doesn't really matter because as long as my signature is the same for if I look at the same object, then it doesn't really matter if that count is 5 or 9 or 190,000. The number that we get here doesn't really matter usually. It's the actual distribution of those numbers within the bucket. So that's one way of doing it. The slightly more clever way, or the more advanced way, or the more complex way, would be to define our buckets, and then if I have a pixel here, let's say I have a pixel that goes in this, that would be this direction, then I include it in two buckets always, but I make it based on how close it is to the center of the bucket. So here, I'll take this one and the next bucket. So let's say this is 20 degrees, this would be 40 degrees. Right? Then this would be 30 degrees. Let's say what we actually add up is 35 degrees. The next one would be 40, it would be 50 degrees. So that angle here is actually closer to bucket number 1 as opposed to bucket number 2. So I calculate this distance and this distance and multiply the 1. So I split up the 1 in order to not just add 1 into both buckets. I split it up and I say 1 minus that distance will be added to this bucket, and this distance multiplied by 1, this distance multiplied by 1 minus this one will be added to this bucket. So here I may get 0.7 and 0.3 in this bucket. That's a more clever approach, a more complex approach, more clever approach to deal with. And if one fits, if I have a degree here, an angle that's exactly 40 degrees, then it will contribute 0.5 to this and 0.5 to this bucket. Okay. It'll then get split up. So that basically fuzzifies our boundaries. Right now we have fuzzy boundaries as opposed to strict boundaries where 89.99999 degrees is going to be bucket number 2, and 90.00001 degrees is going to be bucket number 3. So a tiny difference in angles, minuscule, infinitely small difference in angles may result in shift to a completely different bucket. Okay, and then we could actually implement that, and that is a very clever idea, and it's actually implemented in OpenCV already. It is basically with, if you think about that some more, then you end up with the histogram of oriented gradients, the HOG feature detector, or HOG feature detector, which is a very powerful method that can be used to detect all kinds of objects. So we'll have a look at that one in the next slide. I already have the slides for that one. Just share the slides. Bless you. Now, the original application for the HOG feature detector was actually, it's quite powerful, and in particular for shapes that are not strictly static, but where the particular features can sort of move around. So one of the first applications of it was actually pedestrian detection, detecting people walking. And here we have a similar application. I have some sample images that I created previously, which shows different people walking and talking on the phone. So here is different different people walking, and then the idea would be to recognize people and whatever activity they're currently performing. So you can see that that is a non-trivial problem to implement. It'd be very difficult to come up with a algorithm that says, oh yeah, the edges or the colors are like that or something like that. Like people have different sizes and carrying a baby and different parts of the frame. Even if you look at the edges, you can see, depending on where the leg is in the swing here, you would get different gradients. So a very subtle, very difficult problem that we're trying to solve. So I implemented the data set, and then I can just extract and show 3 people that I selected randomly. In this case, it selected the same picture twice. So I can run it again, and hopefully I get, hey, how come? Do I plot the same guy twice? Random dot choices replacement is equal to false. Replacement, I think. Here, play random dot choice. Okay. on NumPy. Okay, now we have 3 different people. So we use image gradients, calculate the gradient, and here I use Cartesian to polar coordinates function, which gives us the magnitude and angle, and then I can plot it. So that shows the magnitude now as well as the direction of the gradient for various pixels. And then the histogram of oriented gradients is an algorithm proposed by Dalal and Trix that has been shown to work quite or very efficiently for detecting complex shapes like people, other kind of features or objects. But the reasoning steps are the same as what we used for the marathon markers. So he has the gradient information for a single person with slightly more resolution. And then in order to detect them, I break down the area for each person into these cells. And for each cell now I want to find out what the distribution of the gradients are in this particular region. So here that would be basically all 0, right? There's no gradient here. The shape along the inside of the person, it's also mostly black, so not much gradient there. But the legs have very strong gradient returns, the shoes and things like that. So first we normalized our angle to 180 degrees. And then we need to deal with the discretization effects. Now we discretize the angle from 0 to 180 degrees into 9 buckets, which means each bucket is 20 degrees wide. And we want to fuzz the boundaries of these buckets. So basically blurring the cell count. Now one way to actually do that is also to just blur the gradient angles. But this method is a bit more powerful. And so we want to add a gradient, not just to the current cell, but also to the next cell that is closest to, and weigh the contribution based on the distance to the center of the corresponding cells. So here we start out with calculating our histogram of oriented gradients, the number of buckets based on the angle degrees. So the HOG gradients then will be 1 for each block, right? So the number of blocks in Y and X, and then the number of steps that I have, in which case that will be 9. And actually that should be in buckets here, really. So I can set it to 40 degrees and then it would only generate 40, 0 to 40, 40 to 80, 80 to 120, 120 to 160, and then the 80 bucket. So 40 wouldn't work well. 20 works, 30 would work. 30, 60, 90, 120, 150, 180. I think those are the only ones that divide evenly. So now we step through the image, and our feature now is an array with 9 entries. And for each one of those, I get the angle and the magnitude. I normalize the angle to be between between 0 and 180 degrees, and then figure out which bucket it goes into, as well as how much the remainder is, because I need that in order to find out the proportion that should be contributing to the current bucket and the next bucket. So this is the angle of the bucket. This would be the remainder. This gives me the bucket that we're interested in. This would be the contribution to the current bucket. And then I need to figure out where those two buckets are, taking into consideration that if we are at bucket 8, then we wrap around to bucket 0, right? From past 180 degrees, we wrap around to 0 degrees again. And then these are the contributions that I add. And then I set that for each one for the gradients image here. I can calculate it, then I can print out a couple of them. So in my HOG array, basically each one of those is going to be an array of 9 numbers, corresponding to the number of pixels multiplied by the contribution for that particular gradient. And actually, instead of just using our angle, the the HOG feature detector does it slightly differently. We do take the magnitude, so we we multiply our contribution not just by 1, but the length of the vector. And then in a second, you'll see how we deal with that problem that we're mostly interested in the angles. That's what we have here. So you can see here our angles, and our contribution is multiplied by the magnitude of the gradient here. So now I want to plot it. Now that is, we want to try and come up with a nice visualization. So each 9 bucket area, it's supposed to generate a nice view, and I can do that by using a bar chart, which then plots the magnitude of the histogram in these particular ranges. So here I just come up with a visualization of our HOG array. So you can see the 3 areas that I looked at. One of the areas there was no gradient, so the counts are all very low here. Here the gradient, so this would be from 0 to 20 degrees, from 20 to 40 degrees, from 40 to 60, 60 to 80, 80 to 100, 100 to 120, 120, 140, 140, 160, 160, 180. So here the gradients are relatively evenly distributed. In this area here we have very strong gradients in the horizontal, but not much in the vertical. And like I said, the HOG algorithm does take the magnitude, or chose to include the magnitude in their analysis. However, you do have a problem that the that the individual pixels, the magnitude of the vector increases depending on whether it's under the bright light or not, right? If I have a black and white transition, if it's in the shadow, then the gradient, the magnitude of the vector is going to be much less than if it's under bright light. So somehow we need to take that into consideration. One way would be to just ignore it completely and only use the angle. However, that then you have problems with getting random angles if they are very close to 0 magnitude. If it's a uniform region, then basically you can get any kind of direction just by some noise in the image. So then if you multiply it by the magnitude, that would be a good idea, right? Because then if it's a uniform region, the magnitude of that vector is going to be very low. So it's going to have a very small impact on your image. On the other hand, if it's in the bright light, then otherwise you have areas on the bright light will have vastly different magnitudes. So how to deal with that? The developers of the HOG feature detector, they basically took care of that problem one step after what we talked about before. They simply normalize then the length of the vector, because we have 9 entries, right? So I can think of that as a vector. If I want to get rid of the the individual magnitudes or the general magnitude, the brightness in the area, then one way I can do that is to normalize the vector to be exactly unit length. So we can do that. We just apply the normalization to the algorithm. If that normalization is 0, then we set it to 0. Otherwise, we divide it to make sure that it ends up being 1. The length of the vector, then we can show that. So now that's basically the same image that we had before, except that now the scale of the charts here are all the same. Whereas before, this one 40, 100,000 is actually the same. And now I can show the HOG as a ray, like a little visualization. Let's step through and then I can show the image. So now for the different areas, I now get this kind of picture, which is basically the 0 to 180 degree rays for the different 20-degree bucket. So if it's a uniform region, I basically get no response here, so that's just my baseline, so they're all 0. Here I have somewhere there's something that pushes in the 90-degree direction. Here, most of the gradients are oriented in that direction. Here they're sort of split up along the vertical, and similarly here, most of them are in the vertical line direction. So now, and then I can check also the size of those. Now for detecting an object then, the object that we're interested in, the people, would be represented by multiple of these features, vectors. So after normalization, then I apply that and I end up with, in this case, 4 by 8, I think, 32 of these squares that cover the entire person, right? And then each one of these squares is going to be a 9-element vector, right? So here this would be it for the entire person. The ones in red are marked with just values where the feature is greater than some threshold that I set. So here it's 6 by 4. So now, okay, I came up with a pretty clever idea for compressing the image of a person walking into something that I think has a good chance of being able to describe that person, right? Instead of having, how many pixels was that? 32 by 32. So each 32 by 32 pixel area. So that'd be 900 times 3, 2,700 bytes. Is now represented by a nine floating point numbers. So 9 times 4, 32 bytes. So it's a very strong compression that still maintains all the information that is necessary, hopefully, in order to be able to distinguish people from other things. However, it's not really clear what the classification should be. Like if we look for corners, we can say, oh, the gradient in the x and the y direction have to be both strong and they have to be about similar, right? The same. That we can say, but looking at a person, I really have no idea what these rays here should look like, right? These 9 floating point numbers for each block. Right? I can sort of say, okay, well here these ones should be 0 or close to 0. But if people are walking with their arms swinging or they're talking on the phone and I'm trying to distinguish if they're using the mobile phone or not, then that is quite another matter. Right? I would have no idea what that ray would look like if somebody holds a phone as opposed to not holding a phone, or carrying a baby, or pushing a trolley or something like that. So in that case, we can use that to build higher level features, but it does make sense, and the modern approach would be to use machine learning in order to come up with a classifier that as input takes the HOG features and then outputs a classification based on those HOG 9 floating point numbers for a group of areas. So here we have 6 by 4 blocks. Each block is represented by 9 entries. So that's 24, 240, 216 floating point numbers. So I can take the group and I can add it to map it back to the which part they are in, like the 6 by 4 number. And then we can design the training algorithm. So I can simply apply my HOG feature detector for each one of the images that show people walking, and then train it, and I say this is what the HOG feature should look like for the group of HOG features should look like if there is a person walking through. And then I can take the same for people sitting. Okay, so the particular problem here was we wanted to distinguish people sitting from people walking. So then the question is, here would be the HOG features for the negative examples, like the people actually sitting. And I just got those off the internet. So then I can normalize all the images, make sure that they all sit in the same range. And because I think the sitting people, the pixels are slightly stretched. So now I generate my training data. And then the question is, what kind of machine learning algorithm do we want to use in order to distinguish walking people from sitting people? And one that I like simply because it is pretty, it runs very efficiently, very quickly without a lot of training data. And it comes up with good classifiers in general, works quite well, the support vector machine. So here I simply use the sklearn module from Python, which includes a whole bunch of different machine learning algorithms. So if we wanted to, we can also apply neural networks from sklearn in order to train our classifier. But here I used the support vector machines. Now, I'm not going to go through the theory of support vector machines in this class because this is not a machine learning class, but a computer vision class. But since you're in mathematics, you may be interested. This is actually a very clever application of quadratic programming. So it's really pretty slick, and it basically allows us to define various type, either using kernel functions, so radial basis functions, or in this case I use the more traditional way of using support vector machines by defining polynomials up to degree 2 in this case. So it calculates, if you only have two features, x and y, then it will calculate x, y, x multiplied by y, x squared, x squared, y squared, x squared multiplied by y, y squared multiplied by x, all the combinations of those. And it can do that very efficiently. So here we apply it, and then we can show. Now in this case, not surprisingly, it comes back with a perfect classification because I used all my training data. That's not, so you should never actually do that, right? It's, you always want to set aside your training data, part of your training data for validation. But otherwise I would have to cut out more of the people, so I only had 10 people. It was a little bit, if I have more training data, I would do a proper validation. So far, even though it looks perfect, it's meaningless, right? We need to run a cross-validation set, but I didn't actually do that in this case. Group to coordinates. I thought I defined that. Yeah. So here we just need to Yeah, so then here, the same thing. Not sure why I turned that off. Using here, actually, yeah, I did implement it. So here we split the training set into the training data into a test set and a training set. And then we calculate the training accuracy and the validation accuracy. So it's very important that you do that all the time. And then validation accuracy, we had 2 errors. No, validation accuracy, we had 2 out of 8 for the training. But that's because we don't have enough pictures, simply. So taking off one person right now is too much of and you can also just simply change to a neural network classifier with different parameters, and you can try that. And I'll fix up that code later to just use the new function names. For your problem, that's one approach that I think would work quite well for the object that you need to detect. And you can apply that with very little training data. Much less than, I mean, you still need some, obviously, but much less than what you would need for a deep learning approach.
Essentially, it's more motion detection. This one, right? It's like
Not really motion detection. No, things are not moving.
it's
But it can compensate for some motion in the image quite well.
like an image of
And
the
so
wall.
we used it in order to detect the poses of opponent robots.
It's more pose detection.
Not really pose detection, but it's for things that if it's a microphone, if I track this microphone, right, this point is always going to be the same distance apart. The shape of it is not going to change. So there you could use more template-based approaches maybe. I'm not 100% sure about that though, because I think the HOG feature detector may still perform better because of the fact that it can easily tolerate some rotation. The things where the domains where the HOG feature detector is crucial though will be something like tracking this thing, right? Because even though the general shape is the same, it still varies quite a bit when it's flowing in the breeze. Or when you walk, your arms are swaying, right? So if you train a system and the arms are like this, and then you capture the video and the arms are like that, it's not going to be a good match, right? The HOG feature detector basically looks at that and says, well, as long as the gradients of this arm are relatively, so the relative motion here doesn't matter that much. So yes, it was used for detection of kind of deformable objects. That's where it would shine. If it's a non-deformable object, it will still work. If it's a complex shape that has a few moving parts already, then that would be a good application domain for the HOG feature detector. And this is actually, so I implemented it from scratch. This is actually implemented in OpenCV, so you can just apply the HOG feature detector. And it has all the mechanics built in much more efficiently than this Python code here, because it uses C++ to actually implement the HOG feature detector. Okay, good. Then I have to go now, and I'll see you